This is the second part of the topic Lagrange Interpolating Polynomial. In the previous lecture, we have discussed linear Lagrange interpolating polynomials. In this lecture, we will be discussing the nth degree Lagrange interpolating polynomials. That is the Lagrange interpolating polynomials of degree more than 1. Now we can generalize the concept of linear interpolation into the nth degree Lagrange interpolating polynomial. Suppose we have a function f that passes through these n+1 points. First one is x0 f of x0, x1 f of x1, etc. xn f of xn. That is, suppose this is the function y equal to f of x0, f of x, and we have to find an nth degree polynomial Pn of x which satisfies this or which passes through these points. That means this is the point f of x0 and f of x0 is equal to p of x0 or Pn of x0. F of x0 is equal to Pn of x1, etc. F of xn is equal to Pn of xn, etc. That means at the point x0, p of x and f of x coincide. At the point x1, p of x and f of x coincide. At the point x2, p of x and f of x coincide, etc. And at the point xn, p of x and or pn of x and f of x are coincide. So all these points, at all these points, this function f and pn coincides. So such a function we need to, or such a polynomial we need to determine. Okay, in this case, first we construct for each k equal to 0, 1, 2, 3, etc. up to n, a function ln kx with the property that ln k of xi is equal to 0 when I is not equal to k. Ln k of xi equal to 0 when I is not equal to this k, and if I is equal to this k, that is ln k of xk equal to 1. So such a function we are going to find to satisfy these two conditions. First, to satisfy this condition ln k of xi equal to 0 for all I not equal to k, we need in the numerator of this ln k, we need the terms or the factors of this form, that is x minus x0, x minus x1, etc. x minus sk minus 1, x minus sk plus 1, then x minus xn. That is, for example, if I is not equal to k, for example, if I equal to 1, then which is not equal to k, then we have here we have x minus x1 is here, so x1 minus x1 will be there. When I equal to 1, we have ln k of x1. So in the numerator we have these factors. So x1 minus x1 will be 0. If you are taking I equal to 2, here we have another factor x minus x2. So in that case, when we apply x equal to x2, we will get by this we'll get this is equal to 0, etc. But in this product, there is no factor like this x minus xk. There is no factor x minus xk in this product. Okay. Now to satisfy the second condition, that is ln k of xk equal to 1, the denominator of ln k x must have a term like this, but this x is replaced by xk. For ln k x in the denominator, we have this term such that or with the x is replaced by xk. Therefore, like this. So we have the form of ln k is equal to ln k of x equal to x minus x0, x minus x1, x minus etc. etc. x minus xk minus 1, and x minus xk is not here. Then x minus xk plus 1, etc. x minus xn divided by xk minus x0, xk minus x1, etc. xk minus xk minus 1, and here there is no factor xk minus xk, right? So and here xk minus xk plus 1, etc. xk minus xn. For example, if n is equal to 2, then if you are finding ln 1, that means L21, right? Or simply we can denote this as 1. So we have L1 is nothing but x minus x0. X minus x1 is not here because we are finding L1. So x minus x2 divided by x1 minus x0 into x1 minus x2. If you are finding for n equal to 2, if you are finding L2, for L2 means nothing but L22, right? So this is equal to x minus x0 into x minus x1 divided by x2 minus x0 into x2 minus x1, etc. So after obtaining this ln k, this interpolating polynomial is easily described. This polynomial is called nth Lagrange polynomial, and we can define this nth Lagrange interpolating polynomial by using this theorem. That is, if x0, x1, etc., xn are n plus 1 distinct numbers and f is a function whose values are given at these numbers. That is, we have distinct numbers x0, x1, x2, etc., xn, and we are given the functional value of f at the point x0, at the point x1, etc. So these values we are given. Then the unique polynomial p of x of degree at most n exists with f of xk equal to p of xk. That is at these points the value of f and p are same for each k equal to 0, x, 1, 2, 3, etc. n. And this Lagrange polynomial is given by p of x is equal to f of x naught ln 0 x plus f of x1. Next one is f of x1 ln 1 x plus etc. f of xn into ln n x. That is summation k from 0 to n fxk ln k x, where k varies from 0 to n. Also, ln k is nothing but here the general ln k is nothing but x minus x naught into x minus x1, etc. x minus xk minus 1 into x minus xk plus 1, x minus xn, etc. divided by this xk minus x naught, xk minus x1, etc. xk minus xk minus 1, xk minus xk plus 1, etc. xk minus xn. That is, in product notation we can write this as pi I from 0 to n, where I not equal to k, x minus xi divided by xk minus xi. So this is the nth Lagrange interpolating polynomial. If you are replacing the values of ln x, ln1, ln1, etc., ln n, here actually we can replace ln x or ln k by lk itself, right? So if we are replacing these values of ln0, ln1, etc., ln we will get the Lagrange interpolating polynomial as p of x equal to x minus x1, x minus x2, etc., x minus xn divided by x naught minus x1, x naught minus x2, etc., x naught minus xn into f of x naught. This is the first term here. Then plus the second term is nothing but second term is ln1 into f of x1. That is ln1 is nothing but x minus x naught, x minus x1 is not there, so x minus x1, x2, x minus x3, etc., x minus xn divided by here into f of x1, so x1 minus x0, x1 minus x2, etc., x1 minus xn plus etc. The last term will be something into f of xn. Here I equal to n. Therefore, we have x minus x0, x minus x1, etc., x minus xn minus 1 divided by xn minus x0, xn minus x1, etc., xn minus xn minus 1. So in L1 there is not a factor of x minus, this is actually L0. In L0 there is no factor x minus x0, and in L1 there is no factor x minus x1. In Ln there is no factor x minus xn, etc. Okay, so this is a note, that is lnk is simply we can write this as lk also. Okay, now we can discuss an example. Use the numbers x0 equal to 2, x1 equal to 2.75 and x2 equal to 4 to find the second Lagrange interpolating polynomial for f of x equal to 1 by x. Use this polynomial to approximate f of 3 equal to 1 by 3. So here we are given a function f of x equal to 1 by x. So by using, and we are given three distinct points x0, x1 and x2. By using these points, we need to approximate this function into a second Lagrange interpolating polynomial. Okay, so we know the second in the Lagrange interpolating polynomial is nothing but P2 or P is equal to P of x is equal to L naught f of x naught plus L1 f of x1 plus L2 f of x2. So for that we need to find L0, L1 and L2. L0 of x, L1 of x and L2 of x. So we know first we can find that coefficient polynomials L0, L1 and L2. We have L0 of x is equal to, here we have 3 points x0, x1 and x2. So L0 will be x minus x1 into x minus x2 divided by x0 minus x1. Here then we can replace x by this x0 because we are finding L0 here. So x0 minus x1 into x0 minus x2. This will be L0. Now replacing the values of x1, x2 and x0 here, we have x0 is 2, x1 is 2.75 and x2 is 4. So x minus x1 is 2.75 into x minus x2 is 4 divided by x0 minus x1, that is 2 minus 2.75 into x0 minus x2, that is 2 minus 4. So simplifying this, we will get 2 by 3 into x minus 2.75 into x minus 4. So this is L0. Now L1 of x is equal to, here we have n is equal to k equal to 1. So L1 of x is equal to x minus x0 into x minus x2. Here there is no factor x minus x1 here. So divide by x1 minus x0 into x1 minus x2. So replacing the values of x0, x2 and x1, will get like this: x minus 2 into x minus 4 divided by 2.75 minus 2 into 2.75 minus 4. So this is nothing but minus 16 divided by 15 into x minus 2 into x minus 4. You can verify that. Now L2 of x. L2 of x is nothing but, here k equal to 2, so we have x minus x0 into x minus x1 divided by x2 minus x0 into x2 minus x0. So replacing the values of x0, x1 and x2, we will get this 2 by 5 into x minus 2 into x minus 2.75. So using these points, these coefficients L0, L1 and L2, here we get the required polynomial. That is, we have f of so for that we need to find f of x0, f of x1 and f of x2. So we know f of x is equal to 1 by x. So f of x0 is equal to f of 2, which is because x0 equal to 2. So this is equal to 1 by 2. F of x1 is equal to 1 by x1, that is f of 2.75, that is 1 by 2.75, this is 4 by 11, and f of x2 is equal to f of 4, that is 1 by 4. So p of x is equal to this, that is f of x0 into L0 of x plus f of x1 into L1 of x plus f of x2 into L2 of x. So replacing that values of f of x, that is, this is f of x0 into L0 of x plus f of x1 into L1 of x plus f of x2 into L2 of x. So replacing these values, we have f of x0 is equal to 1 by 2, 1 by 2 into L0 of x. L0 of x is equal to this 2 by 3 into x minus 2.75 into x minus 4. So 1 by 2 can be cancelled. So we have this, and f of x1 is equal to 4 by 11 into L1 is equal to this. That is, we get this, and f of x2, that is 1 by 4 into this L2. Okay, we will get this, and you can just verify that this can be simplified to this 1 by 22 into x square minus 35 divided by 88 into x plus 49 divided by 44. So this will be the approximating polynomial of second degree Lagrange approximating polynomial of f of x equal to 1 by x. Okay, that means we can approximate this f of x equal to 1 by x to this polynomial p of x. Now, as an approximation, we have to approximate the value of f at the point 3. That is f of 3 equal to 1 by 3. We know f of 3 equal to 1 by 3. So, the approximated value of 3 by using this polynomial approximation, we get f of 3 is approximately equal to p of 3. So, replacing here x by 3. So, this is equal to 1 by 22 into 3 square minus 35 by 88 into 3 plus 49 by 44. This is equal to 29 divided by 88, which is approximately equal to 0.32955.